Hi, I'm Cece and this is Study in Space, my channel dedicated to taking what I'm learning and teaching it to you. In this episode, we're going to talk about displacement, velocity, and acceleration. But before we can talk about those, we must first define position, which is simply where an object is at any particular time, and is represented by x. Now, when defining position, we often make use of some sort of coordinate system, or a number line, or something along those lines, in order to help us better visualize what our position is. And displacement is a change in an object's position, and it's represented by delta x. The Greek letter delta is used in math and physics to represent a change in something. So in this case, it's a change in position. And you can find delta x by simply taking the object's final position, x sub f, and subtracting its initial position, x sub naught. Also, sometimes you might see it as x sub I. Either way is right. It's up to you how you want to do it, as long as you can keep track of it. And that's displacement. It's pretty simple, just to change an object's position. And now we're going to talk about velocity. First, we're going to talk about average velocity. And average velocity is simply a change in displacement over a change in time, as you see here mathematically and in words. And so it's pretty simple to find. It's represented by v with a bar on top. The bar is mathematical notation for an average or a mean. Let's look at an example. So say we have this car, and this car is sitting here on the number line at 0 meters. And this car is going to drive forward to the right in this situation 5 meters. We can find from this information the object's initial and final positions and its displacement. So it's when the car starts, it's sitting at 0 meters. So our x sub naught is 0 meters. And sorry, this handwriting is messy. I'm writing with a mouse. And then our x sub f, our final position, is 5 meters. And we always have to include our units. Units are very important. 5 meters. And our delta x, our displacement, is our x final minus our x initial. So we have 5 meters minus 0 meters equals 5 meters. And again, sorry for the handwriting. It's not going to get much better. Alright, 5 meters. Now, if, say our car takes 10 seconds to travel this distance, what is our average velocity? We can find that by taking our change in x, which we found to be 5 meters, and dividing by our change in time, which here we're given is 10 seconds. 10 seconds. Divide that and we get 1/2 meters per second. And there we go. You just found the final initial positions, displacement, and the average velocity. But now if we think about it, it's highly unlikely that car was going exactly 1/2 meter per second for the entire 10 seconds. What if we want to know how fast the car was going when it was at 3 meters? In that situation, we would the instantaneous velocity, which is how fast an object is moving at a given point in time. And it's represented by v with this arrow on top. The arrow indicates that it is a vector. And vectors have to be treated specially mathematically because they have both a magnitude and a direction. So you always must include a direction in your answer for velocity. So here mathematically, the velocity, or instantaneous velocity I should say, is not just the change in x over time. It is the derivative of the position with respect to time. And if you don't know what derivatives are, Khan Academy has some great videos. I'm not really going to go into depth about what a derivative is here, but velocity is the derivative of the position function. And then if we want to find acceleration, we're looking at how the velocity of an object changes. So the acceleration is the derivative of the velocity function with respect to time, and it's represented by an a, again with an arrow, because it is also a vector quantity. Let's look at an example together. Say we throw a ball through the air, and the position of this ball can be represented by the function negative t squared plus 7t plus 6. So that's our position function. From this information, we can find all the other variables listed on the screen. So let's start with our final position. We're gonna state that our final position is 0, or our initial, position is 0. We're gonna define our system in that manner. And then we're gonna find our x final. So we plug in time equals 3 seconds, because we're looking at what is happening to ball after 3 seconds. That's why I wrote t equals 3 seconds. So we're trying to figure out where it is, how fast it's going, and how is its speed changing, its acceleration, at 3 seconds. So if we plug in 3 into this equation, we get that our final position is 18 meters. So our ball has traveled 18 meters in 3 seconds. And our displacement, our delta x, is simply our 18 meters divided by, subtracting 0 meters. I'm a bit tongue-tied today. So our delta x is 18 meters. 18 meters. Now our average velocity is our displacement over our change in time. So we have 18 meters. Sorry, this handwriting's really bad. Divided by our change in time, which we're stating is 3 seconds. So our average velocity is 6 meters per second. Now, what about our instantaneous velocity? To do that, we need to take the derivative of this function. So we're going to have negative 2t plus 7 for our velocity function. And to find the velocity at 3 seconds, we simply plug in 3, and we have 1 meter per second. So, to clarify what all this means, at 3 seconds, the average velocity over the given time was 6 meters per second. So if we were to take every instantaneous velocity and look at their average, we would get 6 meters per second. But if we look exactly at 3 seconds, that ball is traveling at exactly 1 meter per second. Now let's do acceleration. To find acceleration, we take the derivative of our velocity function, and that's simply negative 2 meters per second squared, or meters per second. And notice that this is constant. In Physics 101 and 102, I can almost guarantee that you will exclusively deal with constant accelerations. It makes life simpler when you're learning these concepts. So this means that the entire time our ball was moving, its velocity was decreasing by 2 meters per second every second. And that's what our acceleration means. That's all I have for this video. I hope it was explanatory sufficiently. I hope it made some sense. And thanks for watching. Just like to add real quick that all my information either came from my Physics 101 lecture notes or from Openstax University Physics Volume 1 textbook. Openstax is a great resource for free online textbooks. I highly recommend you check them out and donate if you can. I made this using PowerPoint, and I hope you enjoyed. Thank you.